we're going to take all the concepts we learned in previous classes, and we are going to summarize what they look like for the two-dimensional models. Uh, will not be based on derivation. Just basically give you the equation. Derivation are quite uh, similar to how we did for the three-dimensional model. So let's suppose we have a flow. This flow is at angle of attack alpha. Okay, these are the streamlines. Always streamlines go along the flow, and then you have the potential that's actually 90 degrees perpendicular to the flow. So the equations, then the potential flow is given by this equation, and the streamline velocities, stream functions are given by this equation, where your v infinite is equal to u squared plus v squared, and minus alpha is equal to the tangent of this. This is for uniform flow. Okay. So this is number one. Number two, we have the source. Now we did the source in 3D. Let's suppose we got a source in 2D. Now this is completely radial. Okay, so that's why your stream functions go along the radial axis, and your potential functions go in the circular, they're concentric. Okay, so then these are the equations that you get for the source, and the potential for the source, and the stream function for the source. The velocity ur and u theta using your cylindrical coordinates give you q over 2 pi r. This is 0. Note one thing, that qr, your big Q is a volumetric flow, but when you're working in 2 dimensions, then you have this small, this whole thing basically becomes equal to Q, okay? And this small q times z, you could think this as a q times L, so this is actually L squared over T, whereas Q, big Q, is equal to L cube over M. Okay, so this is like V dot, and this will be like area dot, if you would. Okay, area respect to time. Okay, so if you're working with sink, this is number 3. Now all your flows are going inside. That's why it's called a sink. And there's a minus sign because of this sink. The equations are completely identical. The only difference is that we have a sink. Okay? And again, feel free to pause the video and take notes. Number 6. Number 6 is the vortex. Vortex, you can think like a hurricane or a tornado, and is swirling, right? And then you have this only velocities that you have is in the u direction, nothing in radial direction actually. So in this case scenario, what you will have is, this is number 4, vortex, and the vortex is equal to minus gamma and over 2 pi. Gamma is the circulation, as we already have talked about. And this is the potential, and this is the stream function, and your velocity then is given ur is 0, u theta is gamma 2 pi r. Okay. Number 7, this is number 4, this is number 5. So what if you have a source and a sink of equal strength? We only did this, if you remember, but for a small angles, your theta, you want to find the angle P, right? So the angle P will be B minus A, and this is how it's derived. Just from a little bit geometry, if you would. Then your stream function using this equation is given by this equation right here, where this minus sign means that your source goes ahead of the sink, as you can see here. But if there's a plus sign, means that the sink is ahead of the source, so it's inverted. Okay, so that's how you have the plus or minuses. Okay, and So this is case number 6, the doublet. Now we do doublet only for 2 dimensions, and you can see that this is going, everything is kind of going in this direction, and your doublet is given by this. These equations where Q mu is nothing else than Q times L, but we will talk about this later. And your UR is given by this expression, U theta is given by this expression. You can see expressions are quite similar to each other. The only thing different is the cosine and the sine. Okay. And the other case, I would say maybe 6b, sub case of the doublet. Doublet would be if it's at an angle beta, right? It's coming at an angle. Then in such a case, if it's going at an angle, then it becomes beta minus theta. Your equations are basically shifted by beta minus theta. So you can see the equations are completely almost identical. The only thing that will be different is the beta minus theta. Okay. Now, one more thing before we move on. There are a couple of things that we keep in mind, and we work in the boundary condition. And the boundary conditions, when we work, you may want to think that we can take the surface boundary conditions, and we have talked about this before, right? And so we know that v dot n has to equal to 0, and this is the same condition that exists in the potential flow along any stream, right? So you can think that I got a stream and the potential flow is at 90 degrees. So at any point, this is going to be true. So what we can do is we can model the flow with your streamlines with solid surfaces. Now, when we do that, it's a very neat technique that we call mirror method, okay? So basically, let's suppose you have a source at a distance b. So you will be mirrored to the other side with distance b. This is a source, okay, not a sink and a source. They both are sources. And basically, your fluid cannot go through the wall, okay, but you're going to have an image directly on the other side. Okay, so when I do that, in such a case, when we have that, then the combination of the singularities, if I had the source alone, my source alone gives me this equation. Remember, this basically comes from the fact that my equation was natural log of r, and r is x squared plus y squared. But when you shift it at the distance h, then you will have h plus y plus h and y minus h, right? That distance will be given there. So then with the wall, then I have a mirror, and then I have these two components. I have this component of this source, and I have this other component of the second source, okay? Now, let's consider I had this case, right? For the case of a vortex, so I have a vortex, and in my vortex, we have a mirror on the other side. If I have a mirror, then the same idea, right? So I can have a vortex, they're minus sign because as you can see, has a strength gamma, it's my circulation. So it's going in one direction, the other one is going in the opposite direction. Okay, so this one is going positive, so that's why this is positive, this one is going negative. Remember, we define this positive counterclockwise, okay? That's how we defined it. So that's why there's a minus sign there. Now, we can have a doublet, right? Doublet, if I put doublets in this direction, you can see that vertical velocity will cancel out. Because then I have a vertical velocity here and I have another vertical velocity here, and both of them, when I add it up, they actually cancel out. Now, a neat feature of this is if I had a vortex here and I have a wall, they're going to have 4 quadrants, okay? So this is the vortex and has a strength gamma. You can see that this is going this is going clockwise. This has to go counterclockwise with the same strength. And this is going clockwise, counterclockwise. This has to go clockwise. That to think they are mirror of each other, right? And this is going clockwise, not diagonal, okay, has to be across the wall. And then while this is going clockwise, this is going counterclockwise, okay? And also has the strength gamma. And then here, this is going counterclockwise, this is going clockwise, so you can see how the walls work. The biggest application of this would be in the wind tunnel. In the wind tunnel, typically what you have is you have an airfoil and it has a vorticity around that, right? It has a circulation. And the wind tunnel has walls on the top and the bottom. And what in such a case, what it ends up happening is that you end up having an infinite number of vortices. Okay, so this one is a consequence of this one. This one is a consequence of this one. Okay, because this is a mirror of this. Okay, but since I'm going through the wall and another wall, then they all becomes mirrors, and this can go on and on and on, and I will have an infinite number of sets. And this, especially if you're doing wind tunnel testing and you're interested in testing part of it, you might be using stuff like that. So this is kind of the introductory stuff for 2 dimensions. And next we will apply some of these concepts to unique problems.